And topic for today in theory is called system modeling. And I will try to explain you different kind of models of a system. And then I will say most important things about two different modeling languages, Unified Modeling Language or UML in short, and Business Process Model Notation or BPMN in short, and a little bit about approach which is used in software development and which is called model-driven engineering. And what is system modeling? Models are simpler representation of some real-world phenomenon or something in real world, and good models are simple enough to understand, precise enough that they can either explain what is currently happening or can predict what will happen in the future. So most of models should be much simpler than real life, so they distill and crystallize and extract, or call it whatever. They take out all the most important parts of reality and make it simpler, and then even they are much simpler and less detailed than reality, they are good enough to be useful. And there may be very different models of systems, and particularly in chemistry, in physics, there are different kind of models which represents physical reality and considers laws of physics, etc. But in this course we mostly pay attention to information management systems, which I usually call these business process management systems or business process automation systems. And these systems are a little bit different from many different models, is that these describe distributed and discrete systems. For example, there is one very simple non-discrete model which is very simple but good enough to describe and predict many things. For example, F equals m times a, where F is force, m is mass, and a is acceleration. This is not discrete model, it is analog model, because here all these values you can put in are real values, so they may be in any range with precision, etc. And then you calculate them using algebra, which is continuous arithmetics for all the numbers. So this is not discrete model, it is analog model or continuous model. But in business process management, etc., one of good models approach is to make systems discrete. One system here, another system here, somehow related with this system. So this is one bit of something, this is another bit of something, and here is some relation. And it is discrete system. We put it in separate places and we can look on them as a separated things together. And so this is discrete system. Discrete, something like this. And for these models, what I will explain to you, they mostly are tended and oriented to these discrete systems. When you separate systems in parts, in discrete something, and then you look on how these discrete parts are connected and interacts each to other. And particularly for these business process management, information management systems, there are many different notations how to use them, but similarity for them is that they always describe something as separated bits or things from other which are somehow related and works each to other. And when you work on software development, the important part is that in most of cases in real world you do not start from nothing, because you started from nothing in 1970s when you first introduced computers and software in different kind of business and human activities in general. But today, in most of cases, you already have something, and then you need to change something, add something, maybe remove something, etc. So that means that in many cases you need to describe simplified models not only to this new system but also to previous existing systems. And again, if these models are good, they are simply enough for intended audience to understand, but they are precise and complete enough that they show important aspects of the system that you can describe what it is and how it behaves, and maybe predict what will happen when you will change it, extend it, or whatever. And these models usually comes, if we work according to this waterfall and alike models, they usually come after collection of and documenting of system requirements, because in system requirements you mostly just describe and document these activities, what you need to cover with your system, but you actually don't care so much about actual design. As I told you, in simple theory, you don't need to care about design at all, but it is very simplified theory, and because of that maybe stupid theory, because you already have some practice by thinking about system requirements. If you do not care about actual design at all, then you have different kind of interesting problems. How exactly categorize these requirements, how exactly describe and document and show these requirements, because there are many different ways, and each of these ways is more appropriate for some specific kind of system. And therefore, even though you are not required to think about design carefully, you need to think about design a little bit, because otherwise you may document your requirements in not the most appropriate, most efficient way. And then in model-driven engineering process, you actually, so these models may be two different ways. One is just picture instead of text, and another is that these pictures actually are stored in appropriate format with specific editors, that you can actually use them as an input for building your real system, and that is called this model-driven development, model-driven architecture. And then what is also important is that for any non-trivial system, you can look on it from different perspectives. And if you look on real life things like buildings, cars, ships and bridges, then you can look at least from 3 different sides of them, and then you can look inside them, and then you can look inside them in different ways, etc. Similarly, it's for software. You can look from them from different perspectives. One is from outside perspective, so you care mostly about how it works and how it looks from external world. Then you can look inside this system and you see how exactly it is designed and how it works inside it. And then you can describe any system with structural or behavior perspective. And what does it mean? Structural perspective means that you describe structure of a system, and structure of a system is not changing during time if you do not rebuild it. And in old school UML it was called static structure, and static coming from general word means doesn't change during time. For example, you may talk about static systems and do not mix static with statistic. Statistic is a little bit different thing, which uses rules of big numbers to get out something. And then other perspective is behavioral perspective, which describes how system is changing during time or how it behaves, how it works. If behavioral and behaving is not a familiar word to you in English. And then you may describe them in different ways, and as usual, because we can handle written text much easier than pictures, in many cases also design may be described just written text. In most of cases this written text has some structure inside it to better understand, and one of structure may be following. First you mention actors who are using this system, then you describe it, then you say what data is inside system, what it will handle and store and retrieve, etc. Then what is input for it, which in this case is called stimulus, what is output of it, which is called response in this case, and some comments about this. And then you may describe this design like a structured text. But problem with structured text is following, that we as a humans, as a specific species of primates, are approximately 100 million old. And before that, when we diverged from other primates, we have what I call sight, which has graphical acceleration built in. So when we see and look on pictures, on what we see with our eyes in real world, we have accelerator in our brains to see things on top of and in front of other things, and to see relation between these things. So that is our feature. And particularly for humans, if these things looks like face, human face or any animal's face, then of course we see faces much easier than others, because we are social animals, and that's very important feature for us to see other humans very easily. But writing is very new invention. We have history of writing approximately not more than 4,000 years. And if you compare 100 million years for humans as a species and at least 3 billion years for life in general, and life got eyes and understand pictures very early in the evolution, then of course writing is very new invention, and because of that, writing is much harder to understand. It needs much more intellectual effort to understand than pictures. And there are still some people who can't read at all, or who read with struggle, etc. But these humans who can understand what they see, just in general, like this is one thing, this is another thing, they are related in such things that they are hold their hands together or whatever, so this understanding is much easier for everybody. And because of that, when computers could handle drawings and pictures, of course there was big move to start describing things in pictures, because properly crafted picture with the same amount of information is much easier to understand than written text with the same amount of information. Only problem is that you may draw pictures which are ambiguous, hard to understand, because you may use different kind of notations. But here different kind of standards come in that they describe how exactly these things will be shown, and then graphical models are much better than textual models. And starting with history, if you look on these models, initially these models were data-oriented, and the oldest models which showed relations between things in pictures was entity relationship models or diagrams. And these are about diagrams about structured data. And important part about these models is that they introduce a term called entity, and entity is something of interest. And for example, if you care about different kind of business, this means these are different kind of involved parties, and these parties may be represented as a data structure. So data-oriented models talk about structures of data, how they are structured and how they are related. And then relationship, which shows how exactly one kind of data is related to other kind of data. And if you look on, as usual, here are different kind of standards which you can use, but leading standards are approximately two. One is called chance notation and another is crowfoot notation, and I think for this crowfoot notation there's also some family name of initial inventor of it. And how this model looks like. In this entity relationship model, you draw different kind of nodes or boxes, and these boxes may be rounded, but this is just a node in some kind of graph. And these nodes which are rectangular represent entities. An entity is something bigger than attribute. Entities, for example, student, teacher, course, or whatever. So in general, entity is something persistent, so it persists during time. So you do not forget about it immediately after it is not used anymore. And if you look on details, there are these big entities which are like calculated from something, associative entities and relationships. And then there are these rounded or ellipses boxes which show something simple, and something simple is like name, family name, age, date, etc. And then you connect them together in graph. So graphs consists from nodes connected with edges or boxes connected with lines, if you use simplified English. And if you use this chance notation, then you show one entity like teacher and another entity like course, and then here you show its association, you describe type or role of it, like teacher conducts courses, and you add so-called cardinality numbers. That means if you have one teacher from this type of entity, and then it may be related to one or many or other number of courses here. And then if you want to show more details about these data structures, then you add these attributes. So you start with entities, like teacher, and then you add attributes as many you like. And then you can say that some of these attributes is primary key, etc. And then you describe how it relates with something else. So what is good with this particular notation? It is good for conceptual diagrams, because anytime you think, oh, I need to add some attribute here, I just need to find free place in my graph here in drawing, add this particular box here, join it, and so it's very easily extendable. What is not so good is that it's quite verbose and it takes quite a lot of space. And because of that, usually this particular notation is used for conceptual drawings, when you don't care about small details, but you show your most important business objects for this particular system. And then there are other, which is most widely used for different kind of database management tools, called crow's feet notation. And similarities is following, that this becomes to the same thing, but instead of this association here, you just draw a line, and these cardinalities are shown with graphical elements. So one means one element from this entity may be associated with many elements from this entity. You may write as a range 0, 1 to 0, many, or always 1 to 0 or many. And these attributes are not added as a separate nodes or separate rounded boxes, but you add them here, like ID, name, surname, blah blah blah. And then if you need to extend, of course, you extend it downwards here by adding more attributes. And in this notation, here, it is not important where exactly you join box with this line here, because you describe how exactly this association will be created in this diamond here. But here, if you add these lines, actually you need to put them in appropriate fields. For example, if here you have field ID, and here you have this, let's say, teacher ID, then this line should be actually added to this particular field to understand that the relation to use and calculate these relations is used, value for this particular field is used to find out this particular one. So if you will be curious about this, we will go in more details in practical part. And so I consider this older school approach, and it's still widely used because there are many systems which are heavily interested about data structures. Every time you have millions or billions of these entities, or you have millions or billions of gigabytes of data, etc. In most of cases, then you need to care about compact and properly engineered data structures very much, because otherwise you will waste a lot of disk space or persistent storage in general. And therefore you still use manual design for these data structures, because this is most efficient way to get efficient data structures. But in other programming languages, these actual data structures may be generated automatically from different notations. And other approach, which is widely used, is that you do not describe just data structures, but you describe objects. And here, leading standard which is used to describe these data structures in object-oriented form is Unified Modeling Language, or UML for short. So what it is international standard which can be adopted and used without paying any royalties. We will talk about some other standards in details later, but not every standard can be simply used without paying any royalty. There are big classes of standards which, if you use them legally, not illegally, you actually have to pay some fee to maintainers of these standards, because they use this fee to implement new versions of these standards, improve them, etc. But particularly UML, they mostly get income from other things like training and certifying trained persons, etc. So particularly UML, you can download it, you can use it absolutely for free, and that is a good thing. And UML is actually a superset of many other notations which were before that. Around 1980s, 1990s, when personal computers become powerful enough to handle graphics, different kind of ideas emerged how to represent things graphically. And one of initial was computer scientist, family name is Harel, I forgot his first name, introducing state charts. And state chart is just syntactic sugar on top of Turing finite state automata or Turing machines. And then was, I think it was Konrad Buch, which invented participated in inventing other programming language, which was first object-oriented programming language and this Buch notation. And then bunch of other computer scientists which also started thinking about object-oriented approach for system design. But at late 1990s, all these notations were started to organize, see what is similar, what is dissimilar, and UML standard was introduced. And then, when I was studying for my master's degree and later doctor's degree, that was around year 2000, I participated and made my small contribution to organize UML standard 2.0, particularly for behavioral diagrams. So before that was big zoo of different things, but after that there was one leading standard how to describe these things. And of course after year 2000 something, another competing notation was also standardized, called BPMN, or this business process modeling notation. And what is important about UML? First, it is object-oriented. And what is object? So here when I showed you entity relationship diagrams, it describes only data structures. It means there you can hold value for teacher, and it may have ID, it may have name, it may have surname, or you describe it in this crowbar notation with tabular form for these fields. But it's only data. Data and structure of them and relations, how you use identifiers and values of one field to make relation to value in some other table. But in objects, in jargon they say that object is two things, data and behavior. Or you may call it also methods. So in reality it is not so simple, because data is still separated part and behavior is still separated part. But if you look on more abstract way and do not care about details so much, then object represents structured data by itself and also behavior, or what you can use with them. And what is good about this thing is that then it is much easier to use, because you already know what you can do with this structured data inside your object. And UML is very long document. Last time I checked, superstructure is approximately 800 pages, and if you are not working with modeling tools and you do not develop modeling tools by yourself, you are mostly interested about superstructure, which describes different kind of notations which you can use according to the standard to describe things. An infrastructure describes UML itself, and it has also supporting standards, OCL, which standardize these, what is called cardinalities in entity relationship diagram is called multiplicities in UML, but in general this means how many things are related with how many things according to this model. And diagram interchange again is important if you work on tools. And what is important for UML? First, it is object-oriented, and particularly for business process management, for graphical interfaces, for distributed systems, etc. Object-oriented approach of development has proved as one of most efficient ways. Of course, you can still use object-oriented approach and make bad models of system and bad systems after that, but it encourages to use some good practices. So it is platform independent. That means it doesn't care what kind of operating system you use and other infrastructure. It is international standard and free to use. And also it is very precise, so precise that you actually can use UML drawings as an input for your system design, and you can actually make running behaving system just by drawing pictures. And what happened here? And here is UML class diagram. I will explain it in details soon. And it shows what kind of diagrams UML has, most important ones. First, you just draw a diagram, and these diagrams may represent structure or behavior. And structure describes things which do not change during time. And for example, if you would care only about data structures, that would be just like entity relationship diagrams. These are subset of UML, of course different notation, but they represent how data are structured, how they are aggregated, and what is this data part of your system. And then it also shows behavior part or behavior diagrams, which shows how something is happening in system. And that is this dynamic part, which shows what happens during time. And with these two structures, if you use both structural part, like class diagram, and behavioral part, like activity diagram or state machine diagram, in theory, you can describe entire behavior or entire system, what it has and how it behaves, just using pictures. I'm not saying that it is always the most efficient way, but it is enough to describe any system using just UML. And if you describe, of course, that means you can build automatically or manually out of it, and it will work in such a way. And what are the most widely used? The most widely used diagram is class diagram, which shows objects and classes and associations between them. Use case diagrams, which are friendly with use cases of your system specification or related things. State diagrams, which shows how system behaves, and activity diagrams is the same but for distributed systems. And sequence diagram is the same for distributed system where time, precise time, is important. Now about structural models. So structural model shows things what doesn't change during time, and the most widely used in UML is class diagram. Class diagram may be put also in so-called context model, which shows something around your system. I will not go in more details about this. You may also show these like package diagrams, which shows how system is built together. But important thing is that you show boundaries of the system, which means you show what is your system, this newly developed system, or changed system if you change existing one, and what is everything else. And here, example is class diagram, which shows newly designed system and what are different important subparts of the system, like admission, prescription, appointments, healthcare statistics, management reporting, and patient record system. So very high level, that shows what are the most important parts of a system. And this model may also be shown as a package diagram, because in reality these large parts probably are packages of a system, not just simple class. And then it shows similarly to ER diagram. And remember, UML and object-oriented approach came on top of ER diagram just by adding things that you actually show not only relation of structured data inside system, but you show relation of objects inside system. An object is structured data, together its behavior. And here, simple class diagram, which shows that there are patient inside the system and patient record, and it's also always related one-to-one. So one patient has only one patient record. And remember, if you care about terms, in ER diagrams these are called cardinalities, in UML these are called multiplicities. And here is more complicated class diagram, which also adds so-called roles for practitioners who actually design system. These are actually attributes which are used as a fields to get this value to navigate to this other end of this object. So if you look on particular patient and then you look on this general practitioner, then you look on referred by field of it and you see that it is related to patient by this value of this referred by field. And because in class diagram you add these descriptions how you refer to other thing on lines here, again it is not important where exactly you add this line here, because more detailed class is following box. It shows name of the class, it shows fields of these objects of this class and methods of objects of this class, or also methods belonging to the class itself. And so in ER diagram you have to add these lines precisely to particular field like teacher ID and course teacher ID, and then you add this to this particular field, because here you add only these cardinalities like not 1 0 0 1 and like 0 many. But for class diagram, and also one interesting thing that in database design usually tables are called in plural. It usually would be teachers and courses. But in class diagram, class is teacher in singular and course is also in singular. And when you show these relations, which in UML are called associations, then you say that here is teacher ID as a role of this association, and then you can add as a range 0.1 and 0.star. And this is interesting thing if you go into details, but we may discuss it in more details also in practical exercise, that added role to association is the same, only difference is graphical notation, but meaning is the same as writing teacher ID here in as a attribute of this course. So these two things are exclusive. Either you add it here in such way or here. Here of course you show more information because you show that this value of this field is actually used to navigate to teacher, probably using the teacher ID field here. Well, let's say you can add ID here. And then here you say what this object can do. For example, you can create new consultation, you can create new prescribe, etc., etc. And then what is important about object-oriented approach is that with object-oriented approach you can extend your data structures or use simpler data structures to create more complicated data structures. And that is where object-oriented approach is more powerful and expressive, because without just these relations, what are called associations in UML, are this hierarchy, generalization or specialization. So this is different kind of relation, which shows that there is some parent object, which is in most of cases simpler and has less structured data, which may be extended to something more complicated one. And how does it work in practice? It means that if you have doctor object and which has just ID, Then you can extend hospital doctor to hospital doctor, which has ID and let's say ID of its hospital, his or her hospital. Or doctor may be general practitioner, which may have some other data structures added to it. And so such way is very efficient, because if you are allowed to extend these data structures, then you do not have problem with empty places for stored fields, because in ER diagram here everything is just a relation. This means you have to say that some doctors may have references to information about practitioners, but in UML you can say it is not just a relation, but which means it is more specific, more concrete one of doctors in general. And in theory there may be multiple inheritance in UML. In practice, most of programming languages do not allow to do multiple inheritance, and that means that in most cases you have only one parent object and many child objects, and because of that usually you make trees of these generalizations and specializations. And other lines which do not end up with these triangles here are, so if one of line ends up with this closed triangle, then it is generalization specialization. More general classes here, more specific classes here. Other kinds, if you do not add anything, it is just one not detailed association. This means one object of this class is somehow related with one object of this class, but you can add more information to association. First, you can add navigability, and navigability is important if you generate source code of it, because this closed end arrow means that you actually need to create field to store value for it to navigate to this particular object. And then you can add so-called diamonds, which one is colored and uncolored. Colored means that it is so-called strong relation or composition. This means if you have some object of car, it has to have a related object from carburetor class, and their association should be that if there is object of car class, it should always have only one object related from this carburetor class. So this is essential part. This object of this class is essential part of object of that class, or car is composite object, or so it makes this object is composition of maybe many objects here. And of course, if you have composite more complicated object, of course there will be many. So colored, and you can create a tree-like structure. So that means that this composite object consists of composition of many objects from these classes. But if it's not colored, it's called aggregation. And aggregation is something like you put independent objects into a container or bucket. For example, if you have pond, there may or may not be some ducks inside it, but when all these ducks are removed, pond is still absolutely legal object. So it works as a container, and it contains some other objects. And then there are more details about UML. I will not go into it, but there are things called stereotypes and profiles. Stereotype is in general just a badge which you can assign to the class. Like you have customer, and you can add badge like interface. And if you write it as a text, it is these double French brackets opening, French brackets closing. If you are poor man, then you write smaller, smaller and larger, larger here. Or you can change it to graphical element as well, which is allowed according to the UML. But so on that it is called stereotype. But starting with for UML version 1.x, but starting from UML 2.x, this meaning was extended that if you add such badge, it is not just badge like add color to it or whatever, but actual internal structure and behavior of these objects may change. And when you say what kind of profile it is, like then actually when you create such object from this profile, it may be more complicated. So for UML it still shows like blah 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 here if it's written in text, but meaning is a little bit different, and so then it's called profile. And I will not go in more details about that. What else I wanted to say? About more details about associations. So we have some class, let's say class teacher and class, no, not class, doesn't, courses, course. And if you add just simple line, which is not this closed triangle, it means when you will create object of teacher class and some object of course class, they may have some be related. So this is absolutely simple, not precise and detailed, but you know that there will be a relation from object of this or object of that. And by the way, what I say by object, in most of cases, more precise meaning is instance of. Where is difference? For example, in Java programming language, you may say string s is new string. And this means creation of object using definition of this class as a template for it. And in jargon, I can say that this variable s is object, but it is just jargon. So object is just simple way to say things. But in most of cases, when you talk about so-called objects, it is actually instance of. And instance of explicitly is shown in Java by constructing of objects from this class. In other programming language, you don't use this keyword, but here what I mean is that I create instance of teacher class. Why such jargon was introduced, I don't know, but it is very widely used. And then problem appears here that there's also class called object in Java. And now here, if you are not careful, you have big problem, because what is object here? So here, this shows type of your thing, And you see that there is class called object in Java. And when you refer to class called object in Java, then of course you can't use this jargon that instance of some class is also object, because here this is class called object or type of instance called object, and here you create new instance of object class. And then there is actually class called class in Java. And so this is class called class, and here you created instance of this class. So what means instance? Instance means that you go to the declaration of this class, analyze it. For example, look what is internal data structures here, ID blah blah blah, and reserve memory for them to hold these values. If there are some methods here, then of course you allow to use these methods, and then you create this data structure which can use these data structures and which also can invoke these methods described in this class. So instance of means that you use this template here to create data structures and to allow use methods what is inside description of this class. And that is precise meaning of instance. And when you talk about this class C is new class, what you actually are creating, you create some concrete class using definition of this class as a template for it. And there may be templates on top of templates. I will show you in more details later. So that's one thing, but I actually started with other thing. So there was this class teacher, class course, and let's say here is ID, and here is this association. And if you say it is related by, let's say, teacher ID, then this is equivalent of saying attribute teacher ID here, but only thing is that if you will use only this attribute, you will miss this nicely understandable relation that the teacher ID actually refers to some object, some instance of this class. Remember, when I say in jargon object, I actually mostly mean instance of. So that's one thing. Then you can add more details, you can add navigability. Actually, the same would be teacher and this navigability arrow. It shows that you have place where to hold this value to get reference from object of course back to the teacher. And of course navigability may be in both ends. For example, here may be course, and then you may say that it is actually a container. You may add it in more details like diamond, navigability, and multiplicities like 0 till to 1 and 0 till to many. So that is more complicated, more complete description of something. And here these internal properties may also be not primitive types like these attributes, but actually other complicated objects. And for example, if I say that this course is string with capital S, which usually indicates that it is object, not primitive type, then it is the same as like saying that I have course, navigable string. So this inside part is the same as this. Only difference is that here it's more detailed. Here you cannot say what is inside string because you are not allowed to put box inside box. But here you can say in more details that string has length and it has, let's say, chars, which again may be more complicated thing. So you can, if you externalize this reference to this class, then each class may be detailed again about its structured part and about its behavior part. And that's about statical structure. I now look on comments in chat. Did I explain enough about arrows and diamonds, or do I need to reiterate about this? So, let's say we have human, and human will be complicated thing which will be composed of many parts like body, leg and arm, and let's say head. So this is composite structure. When you create a human object, which is actually instance of human class, then it actually must have its internal parts, one body, two legs, two arms, actually I need to describe it here to not be ambiguous, and one head. Okay, I will not show as a range, just one here. And what does it mean? When I create instance of human, like in Java that would be human, let's say age is new human, then inside this construction part, when it is constructed, there should be something like this. New body, new leg, new arm, and new head. And when I will look inside internal structure of this human age, I will see that it also has body inside it, two legs inside it, two arms inside it, and one head inside it. And that is this compositional structure. And if you look in reality, object inside object means object refers to object, refers to object, refers to object. But in business term we can say what this colored diamond means, that there is object inside object, and all these are essential parts of this object of a human class. And again, object inside object in ceremonial formal way would be instance of human has instance of body inside it, instance of legs, two instances of leg inside, two instances of arms inside it, and one instance of head inside it. So that's about these essential parts, or this is composite structure of that. But there may be big aggregation like bucket, which may or may not contain some other things like file, folder, and that's it. For example, this is Amazon S3 bucket, and buckets are very popular name for different kind of storages, and it may have some files or some folders inside them, and of course folders may have files inside them, so here could be one weak aggregation inside the folder as well, but files do not allow it. And also folder may have folder inside it, and I don't know about bucket. So bucket is one large aggregator which can contain either files or folders. Files contain only data, if we go in details, but folders may have files inside them or other folders inside them. And here you should not be surprised about like infinite loop here, because here what it shows is a loop which is actually not loop in for instances, because such loop means that if you create instance A or instance 1 out of this class and instance 2 out of this class, then there is instance 2 inside instance 1. So no loop here, but because both of these instances are instances of the same folder class, then in general that means that at the end 1 here you have instance 2 here, and you refer back to the same class. So it is not infinite loop of something, but it means that for one instance of this end there will be relation to other instance to that end, and both of them of course will belong to the same class. And here of course if you create instance 3 of folder class and instance 4 of file class, so now this contains that, and of course now this is instance of that, this is instance of that, and this relation or association, to be precise, it belongs to that. So now these are two different instances of different classes. And this is about aggregation. You may have empty bucket which do not have anything, and you may have folder which doesn't have anything, and it will still be proper bucket object, proper folder object, because it's not required that they contain anything inside them. They may have, but they also may be valid objects without having anything inside them. I hope that this more detailed explanation made things more clear, not more complicated. Anything else? I take that as a no. Probably more details are also needed before we go to behavioral model about other thing like class person extended to class teacher. So here in class diagram I have two classes, person and teacher extends person. And here it will be important when I will tell you about mof, that if we generate like Java programming language from this diagram, we would have class person, and let's say int id, and then of course we should have say int as a type here, and here let's say string, and then we would have class teacher extends person and string course inside it. So this part extends in one of programming languages like Java, goes to this part in code, and when I write something like I do not have enough place anymore, so you saw this, then if I write in my code somewhere teacher T is new this new part, oops, is this instance of or creation, instance of. And because of this extension, what will actually happen is that for this object, when data structures will be created, first it will, of course, it will create teacher object, but because teacher extends person object, it will have like type teacher inside it with course field inside it, and then it will also refer to the person with its ID. So and when this instance is created, so it will create necessary things of data structures for teacher class and necessary data structures for person class. And if here would be some behavior added as well, then of course teacher could behave like teacher and also could behave like a person. So this also may be important to remember that this means extends, which in some real programming languages becomes like this. But when these instances are created, like in Java it is in following way, then necessary data structures are created somewhere which belongs to the teacher class, and because that extends person class, which belongs to person class as well. I hope that added more knowledge and understanding and didn't confuse you even more. Now about behavioral models. Behavioral models describes system during time or dynamics of the system, and what may happen in system. First, something may go into system, and after that something goes out of it. There may be different kind of regular events, etc. what happens, and the system somehow responds to it. So when something happens, you use these behavior diagrams to describe how exactly something happens. And the most trivial thing which you may use in your conceptual drawing of your system is behavior diagram, which actually do not show much of behavior, and it is use case diagram. And use case diagrams are quite simple comparing to other diagrams. They have actors, which are shown as a sticky man, use cases, which are shown as ellipses, and these things are related or associated with associations and generalization. And association and generalization is the same thing what I already described to you for static structure and class diagram particularly. So just line means association, line with closed triangle at the end means that on the end of triangle it's more general thing, and on other end it's more specific thing. And here is one example. You have sticky man or actor which uses part of your system to transfer data, and then other actor retrieves or receives this data. And here is a more complicated thing. Here it also shows package, and package is large rectangle with this bent corner or like label for it to show like larger part of your system. And then you draw your boundaries of the system, and boundaries of course should be already established when you thought about conceptual part of your system. Everything inside boundary is your system, everything outside this boundary is actors, and if your system interacts with another informative system, it's also actor. So actor is everybody who uses your system, and if it's external system, it's still considered actor in terms of use case diagrams. And then these lines without any rectangles or whatever shows just association, which means client can act or use order food, eat food, and pay for food for the system. So this system is something like automated business process for restaurant. And dashed lines, I didn't mention dashed line. Dashed lines are weak associations or dependencies, and for dependencies they are usually directional. This means that thing depends on that thing. And in this particular case, serving wine is more specific thing of serving food in general. And depending on how you design systems, some of notations and approaches may be comparable. It actually could also shown as an extension. So serve wine may be shown in two different ways. Serve food. So in that system it's shown as this weak dependency dashed line with open-ended arrow, but actually you may be stronger on your opinion and say that serve food is more general case of serve line. So solid line and rectangle at this end, so this means this is more general case and this is more specific case. So how they are interchangeable? This is weaker notation, you are not so sure, because remember, if you use your UML diagrams as an input to generate your source code, here it will actually generate code serve wine extends serve food. for particular class, but here you will have just the class serve wine, and somehow it will also be able to refer to serve food. So dependencies are big things, but here actually they made it again a little bit more strict, and they used stereotype or profile with words extend. So actually here you see that UML is complicated enough that you can use similar things. So, and if you add this profile extend is more specific, it actually becomes much closer to this one here. And that's in general it about use case examples. They are usually used to count how many different kind of general functions or use cases in their terms and meaning you have in your system, and how many different actors. These may be different roles, different types of users, etc., etc. So if you have not counted who does what and who uses what in your system, then of course use case diagrams are good graphical representation of this particular level of details, because it shows very nicely and very easy to understand who does what inside your system. And then an important thing is that for use case you actually don't care about time at all, because it is not so detailed that you see explicit behavior, how exactly these actors are using this system. You just in general say who uses what, who does what, and that's it. But then there are different, more detailed behavior diagrams to show how exactly this happens, and particularly for distributed systems and client-server systems, one of very popular one is sequence diagram. And sequence diagram is interesting in this area that it shows time flowing in diagram explicitly. Time flows either from left to right or top to bottom, and you can know where in which direction time flows for these notations called lifelines. Lifelines are dotted lines which represents life cycle of the object, and objects exchange messages. Open-ended means asynchronous call, closed-ended means synchronous call, and dotted and solid means structured data. This means you can send objects in object-oriented terms, and dotted means just single bit, like done, not done, etc. And if you draw these lines perpendicular to lifeline, then according to your model, interaction is happening simultaneously, doesn't take any time at all. If you want to stress that it actually takes some time, you draw these lines in sloped way. And then when something happens, you may add rectangles on top of these lifelines. And this means that this process takes from here to here. So lifelines are flowing parallel to the time, and in this diagram time flows from top to bottom. And you have distributed system. Here you have actor or the real user which uses patient info system. So he or she opens view info function, which would be method in object-oriented terms, that calls report info in database. Then it authorizes user, check what is the result of authorization. If it is okay, then patient info is retrieved. If it's not okay, then, so here you have these two different modes of operation. One is success mode, when authorization happens successfully, then this part is executed of system. If authorization fails, then it is failed mode of operation and it returns error no access. What is missing here, of course, something should be shown back to a receptionist user here. Otherwise, he or she actually doesn't understand what happened in this system. So these rectangles on top of many lifelines shows these different kind of modes of operation. And I hope you know what is synchronous and asynchronous call. Synchronous call means that here this process is blocked and waits while it will get answer back. If it's asynchronous, it calls something is happening here, but this user can do something else, and then usually you have this callback pattern because you still are interested to know that this process was finished, and you see some asynchronous message like data were saved, data were retrieved, or whatever. And so if it takes more time, then you can draw these sloped lines to show that it actually takes so many time while this message was sent from here till to here. So this diagram is used when precise sequence of events are important, and also, at least in qualitative measures, you want to know how much time some of these processes takes. And that's about sequence diagram. Here is another more complicated. Still everything is happening simultaneously. No sloped lines here to send message. So this means, according to this model, sending message from here to here takes negligible time. So you don't care about time at all. But some calculations here takes non-negligible time. You see that something starts here and ends here. And here again there are two different modes of operation, usually success mode and failure mode. And that's about it. So in many situations there are systems which are very active or reactive. So what is active or reactive? Active means that it acts on something, maybe internal events, and react means that some external events come into the system and it responds. So such kind of system are very easy to describe as a event-based system. Event comes in and system does something when this event comes in. And in object-oriented approach, event usually is some kind of structured message like email, like request from web form or whatever, and then your system responds to it and you can describe it in such way. What this means internally is that if this system acts in such way, actually there is some infinite loop inside this system, and it always checks when some external event is going into it. One another iteration of this infinite loop is happening, and then system goes back to this state and executes some kind of sequence of events when it needs to do it again. And then there are different notation which actually is older than sequence diagram, called state machine diagram. And state machine diagram is graphical representation of finite state machine, and finite state machine is the oldest model how to describe discrete systems. In general, if you have infinite amount of memory, and that means in theory infinite amount of states, you can describe everything what can be described as algorithm with finite state machine. So of course you cannot describe it with infinite states, but it can. What is important is that machine which has finite states still may run for infinite time, because it may run into infinite loop. For example, here you may have state machine which has only 2 states. But if these states are changing from one to another infinitely, even with these only 2 states, it can run forever till to the end of universe. And so these state machine diagrams represent these finite state machines in graphical form. And because of this equivalence principle of notations, as I told you, everything which can be described as an algorithm may be described as a finite state machine, and every state machine may be described as a state machine diagram. And what are important parts of this? So time here is shown implicitly or indirectly. Time starts from one place where there is no incoming arrows. So here it shows order or sequence of events. You know that this event comes after that event and this event comes after that event. And because here it is ambiguous, you don't know where finite initial state may be, you may add so-called initial state with such circle. For example, for this state machine, it may start either from here or from here. And you may draw boxes inside boxes. This means one large state, and this represents some kind of mobile phone. One more general state may be explained in more specific states, putting these boxes inside boxes. And in theory, these boxes should be ellipses, but may also be as rectangles with rounded corners. And then you may add on which kind of event this machine changes this state. And there is more precise notation like precondition / postcondition, so there may actually be 2 dependent events that for system to change state, there may be this and that condition should be true, or this and this should happen. And then it goes to the state according to these lines. And if it also does something, then here it may describe, for example, what exactly happens when system goes to this state to this state. It is not required because state is also something happening, but if you want to make more detailed, more explicit and expressive diagrams, then you may say what exactly is happening when system goes into this state. For example, apply dial tone or apply message or whatever. And then it may terminate with termination state or with abortion state, which is this is successful and this is failed end. And that's in general it about state machine diagrams. There is one big problem with state machine diagrams. In theory, everything, even today's modern systems like internet, etc., may be described using state machine diagrams, because by equivalence principle, everything which can be described as an algorithm can be described as a finite state machine, and finite state machine can be shown and drawn as a state machine diagram. But if you use such approach, then you come into wrong conclusion that internet is the biggest machine created by humans on the world, because to create model of internet using state machine diagram, you have to draw one very large state around all computers of the world and close to the world, like International Space Station, and that's it, because on Mars rovers they do not use Internet Protocol. You have to describe all these connected computers as one large state machine, and of course it is wrong, because it is a distributed system, it is not one very large single machine. And here you see that models may be misleading, and if you want to describe, you can describe Internet as one very complicated, very large state machine, but that would not be good and nice model, because it is not detailed enough, it is not precise enough, etc. So what can you do? For distributed systems, for example, to describe how Internet works, you actually see that Internet consists of many independent machines which exchange data through them. And starting with UML 2 something, they introduced different notation which uses the same graphical elements, but meaning is very different. And meaning comes from computer science and theory called colored Petri nets. And Petri nets are are graphs of directed graphs, and each particular this node represents place where tokens may live. And then these tokens flow through directed edges from place to place. By the way, state machines also allows you to describe parallel execution, because somewhere in these states you may add fork node and show parallel execution. So fork node is following. Some incoming thing, and this is node, it is not line, it is box which is very wide and very shallow, and then it may go into two concurrent states, and then when these states have finished their part, they may go back. So here you have parallel or concurrent execution. If that would be state diagram, you have two concurrent states of this system. So it is allowed. So this is parallel execution, and this is decision, or not parallel execution, with diamond node. Yeah, but for this description of distributed systems and their behavior, they introduced activity diagrams where theory is not based on finite state automata, but on these colored Petri nets. So you have a network of nodes connected with directed edges, and then you have tokens with unique color, and these tokens of unique color flows through these edges like they flow through the river. And these may be also in cycles, and there may be different kind of parallel execution. So when you start parallel execution in colored Petri net, you create duplicates of these tokens, which flows concurrently in different flows. And then when you need to check that everything finished, you can merge them together back, etc. So you see here that graphical notation is very similar to state chart diagram, but meaning is different. So now these nodes represents the something is happens or activities, and these activities represent distributed system. So for state machine diagram, these directed edges didn't represent anything else than just sequence or order of events. But now here you have these tokens flowing through these edges from place to place. And these tokens actually may represent different kind of structured data. In this case, tokens represent orders. Orders may have internal properties like identifier and customer and data items or whatever, and so they are flowing through one part of system till to the other, and here you see exact data flow or exchange of messages between separate parts of system. And so if you want to represent entire internet with behavior diagram of a UML, then of course activity diagram is much more precise, because here you can show each particular independent system, different kind of computers, systems, etc., which sends and receives different kind of messages, and that's how internet actually works. Of course, you can still put box around it and say that this is process order activity, but you see that to process this order, systems have to send and receive some structured data, and that they are separate systems working together. And again, here you may have decisions. So if order is rejected, it goes to the close order and finishes. If it is accepted, then it is filled, and then concurrent activities happens. Or order is shipped, and also invoice object is created, and invoice object is sent to make payment, payment accepted. When accepted payment is received and order is shipped, then this activity can be closed and it finishes. So that is proper way how to show model of distributed systems behaving. And now a little bit about interesting things about UML. UML is reflective language and graphical language. What does it mean? Graphical language means that you draw pictures, but reflective means that you can use language to describe itself. And particularly for UML, you have to study it quite a lot to understand what does it means. But here is simple example for textual language called BNF. And BNF is textual language which also is reflective, because here you have rules of BNF using BNF language itself. So if you are curious, you can study it by yourself later. Here will be link. But important thing is that any human native language is reflective. You can learn Latvian using Latvian, you can use English using English. So it's called bootstrapping process. Then you initially don't know anything, but you have some hard-coded things like discovering faces and reacting and mirroring behavior of other humans, and then you start to understand what is the difference between you and between everybody else, what is house, what is dog, etc. So similar reflective thing is used in UML, and because it is tricky business, there is big part of UML infrastructure standard which describes very precisely how exactly this reflection works, how exactly you can use UML to describe UML itself. So everything in this infrastructure of UML standard is about description of UML using UML diagrams. In most of cases they care about static structure, that means mostly you see class diagrams, and how this works in short. So here you have some real world phenomena, like you want to automate movie renting business. So analog approach without any automation and without models would be following, that you have different set of DVDs. I think this is tape, but maybe it is DVD. And every time you lend or rent to somebody, you write down on paper their phone number, and when you need to get them back, you call them and ask, do you have this, etc. So sooner or later, to get this business properly working, you will create actually model of your business. For example, you may create notice that customer number 123 get DVD number 456, and of course here is real customer having real DVD box, but for you to know where your movies are rented, how to get them back, you create duplication of reality, like with pen and pencil, to count who has what and where they have. And if your model is precise and you look on your pen and pencil notes that customer 123 has DVD 456, then of course it means that in reality this customer has this DVD disc. But if you automate it and create a computer system, software in computer, then you create different model. So you create, for example, entry in your objects, like particular video object with title like Casablanca movie. And so that is your entry inside your running system. So if you see that there is video with title Casablanca, here it doesn't show to which it is rendered, but it means that you see such object collection inside your system. This means you actually have such kind of DVD disc in your office. But this is model of reality, but you can create model of this model. And that means that sooner or later you will have some kind of attributes, some kind of classes representing these different kind of objects, and some kind of instances which actually relates to particular object. So here this instance of an object is very important, because here you talk about object, but in reality it is instance of a class. And here when I say there is some kind of object with title Casablanca, it is instance of a instant class. And you create static structure diagram or class diagram of your different kind of models. And if that business would be completely different, it would be about renting cars or other thing. Of course, this model of reality would be completely different. But model of these models, if you would use UML class diagram to describe them, would be absolutely the same, of course with this precision and with this many details. And then you may ask, but what is model of a model? And this is a valid question, according to MOF. And in general you see that all these called meta classes are actually just instances of more abstract thing called this meta class. And what means instance of? Instance of means that you look on internal structure and behavior of this description, and you create executable, runnable instance or usable instance in general out of this description. And then if you create instance of that, again you look inside its description and other things, and you create other executable or usable thing using this as a template, and you go back. And for example, where is difference between models of models? For example, here is your rental business. If you use UML, you may have only class diagrams according to the UML, but you may use different notation like ORM model, and that would be your model or M1 of this real business, which is this level. Then here you would have class diagram again, but this class diagram will not represent real business, but this class diagram will represent class diagrams of this particular model. And here, let's switch back to UML. We will represent, show class diagram of ORM notation. And here, because we use different notations, this particular detail, so that will be different because different notations are used. But if we try to join them together, we may create another class diagram which shows together everything between that notation and that notation, if we like. And then, what is important about UML? We may ask, but what is meta model of meta model of meta model? Because in theory, we may go into infinite loop. So here may be, so that would be M3, M4, M5, etc. So their idea is following, that starting with this meta M3, if you go up, because it is so abstract that in general this will not be different than that, will not be different than that. So if you go up and up and up, you will not see anything else than just class diagrams representing class diagrams. So here, if you go up, you will not see anything more different because there is no difference in so high level of abstraction. And particularly for UML, here is class diagram representing class diagram, and if you would like to describe class diagram representing class diagram according to the MOF, there will not be any differences at all because it is so abstract that it can be reused in any different specific cases without any additions, any changes anymore. So in general, you have abstract element. Abstract means it is written in italic. And these abstract elements may be just simple comment. I didn't mention comment is box with bent corner. This is comment. Of course, comment is very important in any language, including graphical language. And these may be either relationships or named elements, and relationships may be either associations or direct relationships, and direct relationships may be either generalization or dependency. So graphical representation for this would be a solid line with rectangle, dependency dashed line with open-ended arrow. If it's association, then it is just line, but of course if you go in more details it may have more added properties into it. And named elements are either namespaces or redefinable elements. Namespace may be like a package, and namespace in general means how do you uniquely name elements inside elements inside elements. And class is actually just a classifier, but more specific one, or feature. And feature is also this extension of profiles, or profiles, because stereotypes are not features. And so if you go up, you will see that you don't need any more different things to describe class diagram of this class diagram or meta model of this meta model. So remember that here these all are extensions, That means if you would generate source code of it, that would be namespace extends named element, or association extends relationship. But when you apply this meta model to actual lower level model, you create instance of, you create like new element or new classifier or new feature. That means how you go to meta model to the model or from model to reality. And so this is maybe confusing for beginners, but you should study it, and probably we may pay more attention to it in your practical part of exercises. This idea of MOF actually come from relational databases, because in relational databases this most powerful idea besides relations was that you can describe tables using tables. And if here you see this object-oriented structure of meta models, in databases what you see is you have tables and you have records inside them. For example, here you have table teachers, and here you have records of teachers, two-dimensional table, like here is ID, here is name, surname, and here are particular record. But then this is like your runtime representation, or that would be M1 in terms of MOF approach. So you want to represent physical reality of teachers working in some school, and you have table of these records about all these teachers. But then you may describe a model of this table of teachers, and you see that here, when you describe this table, there is teacher's table, and it has ID, and it has name, and it has surname, and something else. So here is different table, which is easy to transform. What was names of columns here for this runtime table, in this next level it is records or horizontal ones in this table describing table. So here you have one, and you create columns to rows. But then of course you have tables of tables. There may be teachers, and there may be courses, and there may be students. And now you have tables of tables here, and then you say what is meta table of this table. Then of course you see that there is name of table, let's say field, and value of field, etc. So then you start describing what is in internal structure of this table. How can I? Okay, this is this design, but when you need to put many tables here, like courses and teachers, etc., you will actually have some larger table, like name of the table, field, blah blah blah, and again, what was rows here becomes columns here, and then you describe again what was rows here as a columns here. So now you have M3, or table of tables of tables. And that was this idea that if you start describing tables of tables using just the tables, then you create so powerful engine that you can customize for any particular case just using this approach. That in general what you need to do is to handle tables and to handle relations between these tables dynamically. And then, depending on what kind of particular role you are using to understand what actual records and what actual data fields are representing these tables, either it is representation of different table, or representation of a table, or actually representation of real objects, of real teachers or movies or whatever. So precursor of MOF was actually this idea that for relational database systems you may use tables, describing tables. So that's about MOF. And now finally about another thing, particularly for business process, description of business processes, UML is not the most powerful language because it is quite abstract and oriented to system design, not to business processes, and therefore as a competing notation was introduced notation called business process modeling notation. And initially it was a competing different standard, but around 2005 it was also merged together and is now standardized and managed by the same object management group, which also develops and maintains UML as a standard. And what are differences? Differences are that BPMN is more oriented to describing business processes, not to design of a system. And what are these differences? First, all different business processes contains activities and tasks. So activity is container or aggregator of tasks, so it is larger and complicated object containing smaller objects. Then there are participants or roles, which in UML would be the sticky months or actors. Then there are particular sequence of events, and then there are different kind of events and triggers. And here are representation of these things. So in general, BPMN is more expressive, more business-oriented activity diagram. And so if you want to describe business processes, then BPMN is more expressive. And what means more expressive? You can say more, drawing less. And so then, similarly as this flow of messages, they have specific sequence flows like structured message, conditions, defaults. Then there are just associations, and they also introduced like a pseudo states. So here BPMN is merged, and that's why it's more expressive, merged functionality of sequence diagram with activity diagram. So activity diagram was just graph where sequence of events was shown with these directed lines. But in activity diagram, remember, one of axis was time, which showed how it works, and also these blocks of modes of operation, like failed mode, standard mode, etc. And BPMN joins these things together. So here these swim lines are lifelines, when objects live somewhere from here to here, and even though time is not precisely shown here, but implicitly you know for these directed lines that it starts here and ends here. And so these swim lines represents lifeline of particular object. So here swim lines comes from notation of sequence diagram in UML, and this order of events is similar to activity diagrams. So message is sent either structured or less structured from here to here. Then a little bit about model-driven engineering. If you describe your system from behavior and perspective and static perspective, it is enough if you have enough details to describe entire system. So all systems consists of static part, which shows general things which doesn't change, with behavior, which describes how system behaves. And that means that, for example, if you use UML, you can describe entire system just by drawing pictures. In practice, because UML is not expressive enough, similarly as representing entire internet using state chart diagrams, it may be quite a lot of work to do. But if you apply this principle to more expressive programming languages, then you actually can describe entire system just by drawing pictures. And I was participating in scientific project in University of Latvia when I was studying for my doctor's degree, and I participated in creation of so-called MOLA tool. And MOLA tool is tool where you describe behavior of system not in textual language but in graphical language. So there were notations, and this particular is a loop between iteration of these things. So everything when you deal with object-oriented approach of programs is take somehow related objects, do something about them, either iterate through them, create something new, delete something existing, modify something, etc. And everything here was described in this tool, and here there is a screenshot of this MOLA tool designed using MOLA programming language. So here we also applied this bootstrapping approach, that to describe this MOLA tool we use MOLA programming language, which is used inside this MOLA tool. And of course it is a completely different area how you bootstrap, because initially you don't have anything. But it was quite interesting as a scientific project. Unfortunately, because it was not marketed enough and performance was not very good at that time, etc. So it was not my popular idea. But in general, this is one of proper ways how you can describe programs using a graphical programming language. And then probably I will remind it for you in your practical exercise as well. But here will be also lists of different possible tools which you can use to make pictures of your design of your system. And there are two different important parts. One is what we called in University of Latvia modeling tools, and another is just graphical editors. Where is difference? Modeling tools cares about meaning of your pictures, and depending on how good or bad they are, they do not allow you to draw meaningless things. What is meaningless thing? For example, in class diagram, it is meaningless to say that class extends itself. This is not the same as it contains itself, because here when you make a runtime model or create instances of it, there may be different objects created at this end of this association and that end. But this represents, like, remember, this class extends that class, like class A extends A. That is this case, but this case would be class A, and then there is, not class, but A, other end. And of course here I now showed more information, so A, and here, mention at which end, other end here. So these of you who know programming language like Java sees that there's big difference between class A extends A and class A, and A other and just another variable to refer to different object out of it. So that's about modeling tools. Modeling tools care about meaning of your drawings, and depending on how good or bad they are, they do not allow you to draw senseless things, but of course neither of these tools are ideal. And then there are graphical editors where you just can draw anything you like. In general, this means something like Microsoft Visio. They have stencils to have templates for these drawings, so that makes your life easier, but otherwise everything is up to you. And these modeling tools, depending on how powerful they are, actually allows you to generate design of your system with more or less precision, depending on how powerful and feature-rich these tools are. And that's in short it about modeling. So remember that good models are simpler than real life, but still useful because they show important aspects of real life with enough details that they are useful, and that usually, particularly for models of system, you need to have two different parts. One is static structure and another is behavior. If you will have only static part, this means behavior will be up to implementation, so you will not say anything about actual behavior of system during design time. It is also okay. In old school approach, when they had models only of data structures, of course behavior was inside code, not inside models. And leading standard, if you use object-oriented approach, which is leading way to describe systems, is UML. Remember, it is international standard, free to use. Every time you are in doubt, you just Google it, download it, and read, in most of cases, superstructure. Sometimes you also may need to read infrastructure as well. And then one important part is that UML, similarly to entity relationship diagrams, you particularly for static structure, for behavior it is a little bit more complicated. But for static structure it is resolved science. You can use UML to describe UML itself. In most of cases this means you can use class diagrams to describe class diagrams. And if you will be in business of developing modeling tools by yourself or integrating with development tools, modeling tools, and like doing forward reverse engineering, etc., this is one of ideas which you should know, because this is one of basic principles of object-oriented approach, and how can you use the same approach to describe many different systems using the same standardized approach. So that's it from me for now. Do you have any questions or comments?